Okay, amazing. Can everybody hear me? Yeah, thanks so much, Mark. It was great having you in my qualifying exam in which I presented like one just big origami block. I'm like, we're gonna like study this cube from a mathematical standpoint. And I will say like not much has changed except this time we're gonna talk about even more cubes, but maybe a little bit on a high level. So I realize we've got a great crew here today of roboticists. This is a bit more on the computational origami perspective, but we want to know how can we apply new design techniques into robotics applications. And also maybe this will help spark your curiosity and start thinking about new creative ways to implement novel mechanical mechanisms in order to address some traditionally maybe electronic or computational challenges. And here's just to give a little bit of a teaser. Here's an example of, this is an origami hand, and you can see they're all made out of the same kind of origami cube. And if you look at your hand, you'll see that your hand is what's called under-actuated mechanism. So it's not like you're thinking, oh, I'm having a bunch of different joints in my hand, I'm just gonna like activate all my joints. You just go like this, and you can easily get that grasping motion without thinking about each individual joint. And you guys also might be familiar with origami, and you know that there's a lot of emergent properties that comes from basically just placing a bunch of creases onto an origami sheet, and then there's literally millions, if you go online, literally millions of different types of origami that you can fold, and also interesting mechanical properties that can be utilized to a lot of different engineering applications, whether that's in metamaterials or trying to create these like highly coupled structures to get interesting motion out of them. So what we're going to do here is, instead of folding with sheet origami, which is typical, what about cubic origami? Now you can see this is a big design challenge because all of the sides are sealed up. So it's going to have a lot of constraints to the system. And it's entirely a convex polyhedra. And I guess for a little bit of audience participation, we'll have a few people in the audience kind of be some representatives for the water bomb base. So this is actually actually a very ancient origami design that's like kids like to fold these little water bomb cubes out of origami and then like play with them and toss them around as balls. But they also fold completely flat. So this is what it looks like when it's with all the way open, and here's when it's flat. Does anybody want to be the representatives for today? Have it? Okay. Maybe somebody over here. We've got even more cubes. So you guys will be the representatives for today for the water bomb base. You'll see it's actually quite challenging to compress all the way because it causes a lot. You might even tear the cube by accident when you're trying to do it. Actually, there's some similar issue with what's called the square Kressling unit. So it goes here and it folds all the way flat. As you can see, this is also, who wants to be the representative? Do you want to get it? You can see it's actually very, very difficult to fold it flat. In fact, some might even say impossible without tearing the paper. And that's why there's a very common unit called modified Kressling. So you actually pull out some of the space. See how the unit here has some space removed? That allows you to do the same motion, but without tearing the paper. So we've got a good number of examples of the Kressling unit. Anybody want to be representatives? We've got 4 units. So you can see here, we're able to maybe get some people in the back. You can basically it's it's a 1D path, but it'll fold all the way. And then today we're going to also introduce some 4 new foldable cubes. One of them, the sawhorse molecule. So we place this on the side, and then it can become a cube. And then we can also get some roll, pitch, and yaw angles. We've also got a minimal slit cut, so we're cutting a very, very tiny slit in the corner of the cube. We've got the octahedral unit cell, so this is like a cuboid, so you can connect it to each other on a lattice. When you connect a lot of them on a lattice, then you can get an interesting metamaterial property. And then finally, a generalized cuboid. So this has the most number of creases in the cube, and depending on where you place it, you can get 6 DOF motion. You can pretty much change it in all kinds of skew ways. So we've got a few more blocks here. And the one I forgot to mention also is a cube that has a diagonal slit across. So then you can fold that flat as well. It's also rigidly foldable. So if you guys want to pass that around, get some representatives to hold the cube. And ideally everybody here in the center will be able to hold a cube. As you can see, here's 8 different cubes. They've got a lot of different emergent properties. And I think this is just to try to spark your imagination and say, like, what other kinds of cubes could we even make if we change the position of different creases on the surface? And this is just the same principle as regular origami. We're going to place creases on the surface and then just sort of see what kind of emergent behavior occurs. So our goal here is we want to combine the mathematical elegance and the creative design of these foldable cubes with a practical functionality for robots. And I think you might be asking the question, okay, so like what is mathematical elegance? Is that just like mathematicians say that, like, oh, we like something, oh, it's such an elegant solution. And the kind of short answer is yes, but there's also a lot of ways that we can dive into this concept of elegance. And then also secondly, what about practical functionality? Like, you guys are all holding different cubes right now, and you're gonna go to your neighbor and be like, oh yeah, my cube's better than yours because of, and then like fill in the blank there. What is going to be a more useful cube? What is going to be the not that useful cube? Just in general, without like diving down into saying, okay, we have a specific application. What kind of robot do we need to address this application? So one of the things that we can talk about is modular robotics. So one approach is intra-reconfigurability. You don't change anything with the cubes, and you adjust their position with respect to one another. And the other one is actually this is an example from the previous paper, electrovoxels. They do a ton of different steps where they move the cubes with respect to one another to get the chair that converts into a couch. And what we're going to be talking about today is inter-reconfigurability. So you keep the same position of the chair with respect to each other, and then you can get this motion in a lot fewer DOF. So here's an audience participation. So I know you guys are all holding cubes right now. Anybody want to hold up your cube if you think that your cube could be used to achieve this reconfiguration? Anybody? We've got one back here. I think that is the right answer. My eyesight is not quite good enough, but it is the octahedral unit and the generalized cuboid. And that's because those are able to undergo the kind of reconfiguration in order to achieve this. If you were to use that block to represent one of those yellow cubes, you would be able to make that. And this kind of speaks to like one of the fundamental properties. And today we're going to just give you like a primer of like what kind of fundamental properties of origami cubes are considered useful, and what are we interested in studying when we look at a cube? And one of that is the range space. So can the cube, what shapes can it be made into? Can it do roll, pitch, and yaw? Can it reconfigure in multiple ways or have one path of motion? That's the range space. Another one is flat foldability. So in 2D origami, there's a very popular theorem that's called the Miyakawa-Kawasaki theorem. It basically says that if you look at the alternating angles, they should sum to 0, and then you can fold the paper completely flat. So just look at the angles, see if they sum to 0. But it's actually a bit more complicated in cube origami because you've got these 90-degree angle faces. So when they start to compress, they can self-lock. They'll intersect with each other. And there's not really a great deterministic mathematical method to see if it's going to do that. But that's actually a very interesting property when it comes to robotics, because we might sometimes want a self-locking property. Let's say we want it to self-lock into a roll, pitch, or yaw configuration. That's actually quite great for designing in this without having your motor be like, oh, I have to actuate and hold this position if that's the final end state. So here's another audience participation. Anybody want to hold up your cube if you think that it's flat foldable? So can it fold completely flat? Okay, we've got a lot of cubes in the room. Looks great. And yes, most of the cubes are flat foldable. And additionally, we've got 2 cubes, the sawhorse molecule and the generalized cuboid, that are not flat foldable. So even if you pushed it, you would start to kind of rip the paper and start to reduce the structural integrity because it's got that self-locking capability without going all the way flat. So here's another property. We want to know if it's flat foldable or self-locking. And then finally, we've got multi-stability. So I don't know if you've guys ever heard of a Venus flytrap, but it's a carnivorous plant, and most plants like aren't known for like attacking stuff. So they don't want to use a lot of energy, and they're just kind of sitting there. And then they've got a multi-stable mechanism that's like a little, a curve that goes from out to in. And then it'll snap to close on the fly. And that's kind of similar to how this emergent property happens in a lot of these cubes, is because, you have to like input an energy barrier, and then it's got these 2 stable end configurations. So as you can see, kind of like the Venus flytrap, you might be able to save energy if you're applying it to a robotic situation, maybe with a soft actuator where you don't want to use too much actuation energy. You just want it to like kind of toggle between these 2 end configurations. So audience participation, anybody have a cube that you think might be a multi-stable cube? Yes, we got enthusiastic in the back. Anybody else have a multi-stable cube? So these are all multi-stable, even though some of them are pretty difficult to actuate. The reason why they're difficult to actuate is because they have such a high energetic barrier. You almost have to like really fold the cube in order to get it to actuate. So this is our final property, rigid foldability versus multi-stability. If it's rigidly foldable, all the sheets don't have to fold, or don't have to have like an angle in them. It can do it completely rigid. So basically here, we've got a toolkit of origami cubes. I'm not trying to say like, oh, rigidly foldable versus multi-stable, like which one is better than the other. It really is a toolkit, and it has to do with what kind of properties that you want to have. But what we really want to do is expand the toolkit and also understand some of these properties. Does anybody have a time? Oh, it's up here. Okay, amazing. I don't want to like run out. So I guess I'll kind of go through just like briefly a few of these. This is not like the full contribution. If you're interested, you can read the paper and try to dive in a little bit more, but I'll just show like a couple things that I thought was cool about each of these different cubes. And I think they're definitely interested, like different in properties, but we'll start off with talking about the sawhorse. So just to jog your memory, this is the video from the beginning. You can see that they're all made out of the same kind of cube. And we also did a couple different, here's some other demos. For example, we have a concave and convex surface that toggles in between each other, as well as showing kind of an alternating zigzag lattice. But you can see here, they're all made out of different embodiments of the same cube. So as you can see here, we've got the multi-stable effect. We can do roll, pitch, and yaw, and we can also do tunable joint limits. So when you push down on the cube, it can either push down a little bit or it can really compress all the way down. And actually, one interesting thing to point out is that the sawhorse decomposes into other cubes. So we've got the sawhorse. You can place these vertices anywhere within this region. It really is a topology that shows how they're connected to each other. But if you put them all the way in the corners, you got the modified crestling, which I think some people, it's the block that doesn't compress. Somebody here has the crestling, or you can put the vertices and combine them to the center, and then they actually become the water bomb, which is the 6th vertex in the center. So you kind of have these decompositions. And in this way, we call this a molecule because it's like the general topological space of like a specific embodiment, which is the unit cell. So you basically put the vertices in a certain location, and then you've got a different property. We did a couple different models of this, thin deformable panels. So this is like a 2D model, but also thick rigid panels. Thick origami is actually a huge challenge because when it starts to bend, then they intersect with each other in a weird way. So you have to tailor in gaps to the model. And okay, now I guess we have a game here, higher or lower. So we talked a little about the energetic barrier. That's how difficult, it's kind of like how difficult it is to compress, or how much energy do you have to put in the system. So if you have a motor on your robot, you have to put a big motor, or do you only have to add a teeny tiny motor that easily just adds a little bit of force. So how about, I like when audiences say things together because it's funny. Stiff hinges or less stiff hinges, which will give a higher energetic barrier? Yeah. How about rigid panels versus less rigid panels? Rigid panels. Yeah, rigid panels. And how about stretchy hinges versus not stretchy but flexible hinges? Okay, this was actually a trick question, and that was actually a pretty interesting finding of our study. We looked at the face material and the hinge material and looked at do we want to have rigid or flexible, stretchy or non-stretchy, and then we created mathematical models for both of them in order to accommodate both the amount of face bending as well as the amount of hinge bending in the model to see if we could sum them up to predict what kind of energetic curve that we would get. So for face bending, we have rigid versus flexible, hinge. You can see, interestingly enough, the non-stretch is like a linear curve, whereas the stretchy hinge we modeled as an exponential curve. And this ended up being what we saw in the experimental results, that in the small displacement region, then the contribution of the stretchy hinges isn't as much, but as you start to really push the limits of your displacement, then you really see a strong component taking over of that flexible part. Here's another question that has to do with the geometry. No, so not the materials, just the geometry of the block. Which one causes a higher energetic barrier? More twist or less twist? Yes, more twist. You can see it starts to decompose towards the crestling unit. How about a larger range versus a smaller range? That's the H parameter. Yeah, larger range. And you can interestingly see that the higher the H parameter, the more energy dissipation you also see for the voxels. And if you were to chain them all into a line, you can see that when you apply a constant force from the top, first the orange block buckles, then the yellow block, then the light blue block, then the next lightest blue block, then the most next lightest blue block. It all goes in the order of overcoming these energy barriers that get subsequently larger. And here's another thing. Hold up the block if you think yours has the lowest energy barrier of anybody in the room. So this is the person who's been like playing with their block the whole time of the presentation. Yeah. That one definitely does have a very low energy barrier. And that's also something that we found in our studies, is that the more that you cycle the block, if you have a paper block, then you can cycle it, but then after around 200 cycles, it starts to kind of even out. So it really shows like there's also a material degradation property in addition to just the geometric and the fundamental material parameters. Now I'll give a little, a brief overview of some work in adding a minimal slit to the block. So here's an audience, like a memory test from earlier. So you can hold up your block if it was geometrically multi-stable from earlier. Some people, yeah, we have a lot of multi-stable blocks here. They're not rigidly foldable. And now how about if your block is completely closed, like your block has no cuts or openings in it? Yeah, it's the same group of people. So I wonder why that is. Well, that was shown in 1813 by Cauchy, who proved that convex polyhedra that are constructed of rigid faces and hinged edges are in and of themselves rigid. And even if you add so many different creases to it, it'll still be rigidly foldable. However, Abel in 2014 was able to show that if you cut the surface, it will remove this property, and we can add a minimal cut size in order to rigidly flatten a tetrahedron. So the way we do this is we add a teeny tiny cut, and then somehow we are able to completely remove this super large energy barrier that we previously had by making the minimal small cut. So I think somebody here has the diagonal cut block that has a really large cut that goes all the way across the face. What if yes, right here, we've got the big diagonal cut block. What if we made one that is a super small cut block? So we basically start with the traditional water bomb, make it rotationally symmetric, and then we add a few different cuts and creases. And the methodology that we use for this is parametrizing the cube. We solve for the minimal cut size, and we find that it's 8.6% of the edge length. So that's a super small cut compared to the size of the edge length, and much smaller than the large diagonal. So this is just a computational equivalent to the analytic model, which is the minimal length. Here it's too short. Here it's too long. So just right is the size of the cut that is basically able to, when you fold the block, it'll be equal to the original distance between the endpoints. So you don't try to like start folding it and then you separate it more than you originally started out to. Another kind of corollary to this is changing the number of cuts in each cube. Can we do a programmable multi-stability? So instead of having like all 4 cuts, what if we do like 1 or 2 or 3? And this also has kind of a similar effect in that we're able to reduce the energetic barrier by adding more and more cuts to the block until you finally have all 4 cuts, which is both theoretically rigidly foldable and is also shown in the experiments as well. And finally, I'll talk about what happens when you combine multiple of these blocks together. And one of the great examples of this is the octahedral unit cell, because that is the one that has multiple equal ways of reconfiguration. And it also kind of has this like stiffness to it that prevents you from like collapsing it entirely. So we want to know how the individual units reconfigure, and then also how they create tessellations together. So in terms of how they individually reconfigure, there's basically 3 pathways. You can compress it in the X direction, you can compress it in the Y direction, and you can compress it all the way down in the Z direction. But because there's an internal structure, what you can't do is push all of the corners together. It would make something that doesn't have a lot of rigidity, and we want to really enforce like, okay, here are the XYZ pathways. Those are the only pathways that you can follow. And we do need to have a kinematic model for this if we're going to like do the next step and put it into the generative model to create the tessellations, but it's actually a little bit challenging. And the reason why it's challenging is because if you have a height h, then you can have more than one state. So for example, here we've got, let's say we have h equals 2, then it could be completely flat, or it could be like rotationally symmetric. So it just makes it a very complicated system to try to solve. But here's just a random idea that seems completely unrelated, which is looking at the geometry of a sphere passing through a plane. When you have a sphere, it passes through the plane, there's a circle that is formed at the intersection, and the circle gets bigger and smaller, not in a linear way, but in a way that's proportional to the geometry of the circle. And we can use that exact same geometry in order to solve this system. Because if we place the four corners of the cube, and we place at the like intersecting plane, and we place the A vertex at the center of the sphere, we can actually get exactly the same system when the block moves around. And then this also allows us to satisfy the property of different, of like making that tube shape and making a center shape, because we can move the position of the C vertices around that intersecting circle. So I know this is like, it just showed a lot of math, but I think it just kind of goes to show how when you're trying to characterize these systems, there might be some interesting and surprising analogs that you can use in order to try to understand how this like very, very coupled geometry can distill down into something that's more simple. And we also did some generative modeling, which I won't get into too deep with, but here's just a few different tessellations that have different properties. So this one can compress in all three directions. This one's fully rigid, like if you push on it, it's completely incompressible. And this one has like a really weird folding method where it folds in one direction, which is like this. So it's this structure, but then when it folds flat, it can only go one way, and it's like, so I think it's just kind of a very interesting example of how you can create these generative models and then sometimes have a surprising result. So, okay, what's next here? We talked about like 3 different cubes. We have sawhorse, minimal slit, octahedral, and kind of briefly touched on a few other like budding work. One, I think, big vision is a pretty large challenge, which is a 3D shape matching problem. So if you want to create a robot that is able to do shape shifting, like we say, oh, here's one shape, here's another shape, and we want both of those shapes to be like energetically minimal, then I think this is like one potential pathway, just because it's a super coupled system. And I think another big vision that we can start to dream of is, this is a paper from 2013 from Hodlipson's lab called Evolutionary Design of Robots. And they completely created these running robots just out of cubes. And this was using an evolutionary algorithm where each of these cubes had a different property. So if we have even more tailored cubes, you could just imagine how this kind of evolutionary design of very complicated systems could start to take hold. So thank you so much for coming today. And we have 6 more minutes for questions.
I have a question. I'm very curious about like you basically provide a different way to consider the construction of robotic structures. One thing I'm especially curious is in the last modular design where you have one shape and repeated that for many times, you build a larger structure that can move and show some macro behavior. I wonder how damage on some of the modules. Like if some of them go through wear and tear, or the robot gets hit, or some part of the body is damaged. Would the overall behavior change suddenly?
Yeah, that's a really good question, because that was actually like one part that we did like incorporate into our model, which is looking at the number of points of connectivity from one block to another. So we had a block, and we could have different degrees of rotation, but as you can, it's hard to visualize without the visual, but basically when you have 2 blocks together, you might have one that only has a few points of connection, and that's not a very strong connection, whereas if you actually put like a 90-degree rotation to connect them, it's very strong. So if you look at the total number of points of connection of each individual block, you can kind of use it as a proxy to see if it's like a very rigid structure or one that's not. And we also just like threw out ones that we thought, okay, this is just not enough points of connection. It's not going to be structurally stable enough. Yeah, thanks. That was a great question. Mm-hmm.
How difficult is the control of like those big robots, like that you make with a bunch of origami cubes?
I think one of the goals for control is to do it in as few few actuators as possible. So one way that we could do that is like for a tendon actuated robot, you can control, like you can try to route a tendon all the way through it. So if you imagine like the Hodlipson example previously, maybe you could say, okay, we can route a tendon here, we can route a tendon there. That's not a problem that I've solved, but I think it would be really interesting to try to optimize on that. But as you can imagine, if you like were to individually have control over each one, then you would have to like route to each one. Like if you're in the bulk, that might be difficult.
A little bit similar, but when we're talking about the connection points and where you're sort of aligning the different parts, I guess, when they connect in, I guess, like a given way, I'm assuming you pick sort of a given set of connection points for each of those shapes. But is there like, I guess, a way to do on-the-fly reconfiguration of like where those connection points occur, or is it sort of set when you sort of do the tendon structure, I guess?
Yeah, that's a really good question. And I think that's like one of the very fundamental principles in like looking at intra-reconfigurable versus like inter-reconfigurable structures is that if you want to attach and detach, then you have to make a locking mechanism in order to do that. So in the generative design, like if you're at design time and let's say you don't want to make this locking mechanism, like, oh, it's too complicated to make the locking mechanism. We're just going to focus on design time. We basically just like have a grammar that's like 8 different options of ways that it can connect, and then you can like apply one of those parts of the grammar. But if you're at design, if you're like trying to cause something to like attach together on the fly, then at least in these designs, they don't have like an automatic way to do it rather than actuating it like individually.
I have a question. So I'm so curious, like, can those soft robotics take some medicine and help the people to like cure the disease?
Oh yeah, I don't know if you're familiar with your jobs lab, but as far as I don't want to like speak for the lab, but what I heard recently is that they were able to do some tests with a pig and be able to deliver medicine using like a six hexagon version of the Crestling unit in order to like magnetically go through the pig. So yeah, I'm really excited to see if that project will have some good results.
Yeah, one question. So assume if there's like a perfect locking mechanism and reconfiguration strategy, is it possible to have like basically one cube that can turn or convert it into like any type of origami cubes?
I think like on a theoretical basis, then you can say, okay, we're just gonna like put as many different creases into it as we want. But one challenge with that is, I guess, one on the manufacturing standpoint, it's the more creases you add, the more like, especially if you're doing like a rigid and a flexible manufacturing method, it just makes it more things can break because each hinge is a liability. But then also, we would just want to be able to, I think one like mode of operation here is to try to design the simplest crease pattern that's possible to do a specific application and not like add addition, like try to do it with as few creases as possible.
So last year at the seminar we had Cynthia Sun talk.
Oh yes.
And I'm trying to integrate what I've just learned from you today, what she showed and has shown for origami optimization. It seems like you have you restrict yourself to the origami cube as your sort of basic primitive, but then you do a much wider range of modifications to it than I think she's willing to accommodate in her optimizations. Do you have anything to say about that?
I haven't gone to the talk. I did see the talk going out, but I
But you've
unfortunately missed it.
seen like some of her work, I'm sure, with the origami optimization of robotic design.
Yeah, I guess it's like, I do think that one like challenge, like if you were to approach this from a like heterogeneous perspective, I think that would be really difficult, especially since like I think the best way to do that is just like by doing a grammar and like having like evolutionary approach. I think one thing that I'm like very looking forward to in the future is looking at the cuboid voxel with more depth, because I think that it's able to really accommodate some of the 6 DOF changes that are needed just to like reach a wider space. Because I just did feel like, I think like working with the sawhorse voxel and like the other 2 that I shared today were much more limited when you're like in a 6 DOF space. So I think that I'll probably continue to take like the homogeneous approach, but I mean, I think that there's definitely potential either way.
Curious how like conceptually is origami structure like related to the chemical structure? Because I think it's kind of similar to like
Yeah. That's actually the reason for the name for the sawhorse molecule is because the creases are in the sawhorse. If you've ever taken organic chemistry, like the sawhorse molecule is it was like, that's where I got the idea for the name, because it doesn't really matter like where exactly the atom is with respect to each other. It just matters the connection between the two. And that kind of like emulates the theme here. Yeah, that was like a good, thanks for pointing that out.
Okay, one question. I'm curious what you think are like the best fabrication strategies for going from like some of these voxels to something using a robust setting.
Yeah, I think one of the ones that, at least the two that I've looked into the most are looking at heat lamination. So basically having like the rigid sheets and then the flexible hinges. And the other one is using like a double-sided adhesive, because then you can do it all like in a laminar fashion. I guess if you want to be really robust, you can like actually like put in a metal hinge, but I haven't gotten that route. It's just a lot of components. I think that's all of the time. Thank you so much.